Okay, gang. This section is 6.3, and we continue with what we were talking about before on probability, take it a step deeper and, calculating probabilities of events. And first of all, we're going to start talking about experiments with equally likely outcomes. For example, if I was going to toss a coin, unless the coin was weighted somehow, you would expect half the time to be heads, half the time to be tails. Or if we look at my intro here, we're going to roll a single die, which means you've got 1, 2, 3, 4, 5, 6 different things that could come up. So supposedly each of these, the probability of a 1, what do we got here? Oh, if we had an odd one, we wanted to get an odd number, the probability of getting an odd one. That means we would come up with a 1, a 3, or a 5. So if I wanted to find the probability of being odd, all I'd have to do is take the probability of a 1, the probability of a 3, and the probability of 5, and add them up. Since they are equally likely, the probability of 1 is 1/6, the probability of a 3 is 1/6, and the probability of a 5 is 1/6 also. So if I add those up together, that gives me 3/6, which of course is 1/2. We always put it in lowest terms. So since they are equally likely, I'm going to change this a second. Since they are equally likely, all I really needed to do is say, well, how many elements are in the event? So we were talking about being odd. The event is odd, and there's 3 things that could happen. So in this one here, that's simply going to be 3 over the number in the sample space. There's 6 different things that could happen, so 3/6 gives you 1/2. So instead of going back and adding all those fractions, all I got to do is think of the number on each one, which now takes you back to what we were doing last chapter, finding the number of things that happen. So we're going to be able to use things like permutations, combinations, and factorials to come up with the answer. So that's what I'm saying right here. Instead of finding each of the fractions and add them, all I got to do is say how many different ways are there being odd over the total, which is 1/2. And a lot of times I keep going back to this. The probability of an event is really the number of the good things that could happen out of the total. So when I said odd, getting a 1 was good because it was odd. Getting a 3 was good, it was odd. And getting a 5 was good because it was odd. So things like 2, 4, and 6 would be bad things. So the number good was 3 out of the total, which of course is 6. So I want you to start thinking this way. That's what this section is about. Okay. Next page. So you can see it bleeds through, so I got to watch my pages on how I do this. Okay, here's page 2. So if I'm selecting balls from an urn, and an urn, I don't know why they keep going back to that. That started back in the Greek days, but think of it as just a bowl or a bucket or something. But inside that urn contains 8 white balls and 2 green balls. And we want a sample of 3 balls. What's the probability that contains white balls? Only white balls. So we're going to pick 3 of them, and they're all going to be white. So first of all, let's look at the bottom number. Okay, I want the total different things. So you've got 8 balls in there. This is a combination of 8 picking 3. I'm sorry. A combination of 10 picking 3, because it's all of the 8 white and the 2 green, and that's going to give me some number. Okay, I'm going to get my calculator ready. So let's see. Clear, we want a combination of math. Oops, 3. Combination of 10 picking 3 is equal to 120. So that's the bottom number. On the top, now we want them to be all white. There was 8 white balls altogether. And I'm going to pick 3 of those. So that's a combination of 8 picking 3, and that number is going to be 56. Let's see, if I was going to put that in lowest terms, I know 4 goes into this one, 14 times. 4 goes down to there, 30. Oh, I'm still not there. I can take 2, that's going to be 7 over 15. That would be my final answer if I was doing that. Now, it's not quite that easy because there was a part that I left out here, and I did it on purpose because I was trying to show the easy way first. But the second part of this, for the green balls, there was 2 green balls, but I wasn't picking any of those. That's going to be automatically 1, so it didn't make a difference. Now that will come up later, and I wanted to show you now. Okay, in B it says, what's the probability that the sample contains 2 white and 1 green? So we're going to set this up. It's a combination out of the 8 white. We want 2 of them, times the combination, there was 2 green, and I'm going to pick 1, and the bottom is still a combination. There was 10 altogether. This is the total, picking 3. And when you do this, things to notice is the first number here is an 8. The first number there is a 2. 8 plus 2 gives you the first number here, which is 10. The second number here is a 2. The second number here is a 1. 2 plus 1 gives you the 3. That will always be true when you're setting these up. Now, we already know the bottom number is 120. So up here, combination of 8 picking 2. I can do that in my head. That's going to be 28 times a combination of 2 picking 1 is 2. So when I multiply that, that's going to be 56 over 120, which just happens to be the same one there, so we know that's going to be 7 over 15. So the important thing for you to get right now is to be able to see how to set this up in that big formula. And then once you get that, then you're going to go back to your chapter 5 and use the rules there to evaluate those. And then once you get here, you're just putting in lowest terms. Okay, let's look at example 2 that I got down here. These numbers are going to be a little bit tougher. Okay, a bin in the hi-fi department of Building 20. Building 20 is like a store name. It's a bargain outlet. It contains 100 blank CDs, of which 10 are known to be defective. If a customer selects 6 of these CDs, determine the probability 2 of them are going to be defective. Okay, so right away, my event would be 4 good plus 2 bad. Where did the 4 come from? Well, I was collecting 6 altogether. So if I knew 2 of them were bad, 4 of them had to be good. So that probability, and that's what I'm doing here, the probability. Let's start with the bottom because it's a little bit easier. So how many did I have to begin with? I had 100. And I'm picking how many? 6. Now, later on, that's going to give me some number. Okay, on top, when it talks to the good ones here, I want 4 of them. How many goods were all together? Well, 10 were defective. So if I take 100 and I subtract 10, that's going to give me 90. So it's a combination of the 90 good ones. I'm picking 4 times of the bad ones. There was 10 bad, and I'm picking 2. Run a space here. Combination of 10, picking 2. So if I go down here, I don't even know if I can do this on my calculator. Let's see. Let's try it. 90 combination 4. Yeah, that's a tremendously big number. 2, 5, 5, 5, 1, 9, 0. Times, then we got a combination of 10, picking 2. That's 45. And then I've got to divide the whole thing by 100 combination of 6. And that number is 11920524400. Now, it would not make any sense of putting that into lowest terms. The numbers are just too big. But what I would tell you to do, if you really wanted to use your calculator, if you take, now you probably can't do it unless you got a graphing calculator, but the best way is you take, you're going to, these are the actual keys you're going to put in. You're going to go 90, and then the combination key, 4 times 10 combination 2 divided by 100 combination 6. And you can put all that in one time and come up with your answer. So let's see if I can do that real quick. So that, bear with me. I'm playing more than anything else, I guess. Okay, so this number works out. My calculator says 0.096458469 And we would never leave an answer like that. That's too many decimals. It would make sense, and this is what they usually do when you get into statistics. They'll round to 4 places. So let's call it 0.0965. And that would make sense to write that as a decimal. It would not make sense to try to write that as a fraction in lowest terms. Okay, so however you'd have to go to do that. That's kind of a difficult problem, but at least I showed you. The important thing is knowing how to set it up. This part right in here. This is the part you're actually learning right now. Okay, here's my third example. So selecting students, a professor is randomly choosing a group of 3 students to do an oral presentation. In her class of 10 students, 10 are on the debate team. What are the chances that the professor chooses at least one of the debate students? At least one. So that means we could choose either 1 or 2. Okay, so if we choose 1, we would set this up, a combination. Okay, now how many are on the debate team? 2. And we're going to pick 1 times the combination of, that means there's what, 8 that are not on the debate team, and we're picking that should be a 1 there. I mistyped it. Okay, and 8 picking 1. So you got 1 on the debate team, 1 not on the debate team, over a combination of 10 picking 2. Remember, 2 plus 8 gives you 10, and 1 plus 1 gives you 2. Okay, or means add. So we're going to get a number here, then we're going to add it to over here. Now we're talking about 2 of them of the debate team. So there's 2 on the debate team. We want to pick both of them. And then out of the 8 that are not on the debate team, that would be 0. And on the bottom, that's a combination of 10 picking 2. Okay, so combination of 10 picking 2. Give me a second here. I'll do that real quick. Okay, so on the bottom here, I'm going to have 45. Over here, it's 45. Combination of 2 picking 1, that's 2. Combination of 8 picking 1 is 8. So that gives you 16 over 45. Over here, combination 2 picking 2 is going to be 1 times combination 8 picking 0 is 1. So you're going to have 16 plus 1, that's 17 over 45. Okay, now that may or may not make sense to do that way. Leave it as a fraction, or if you wanted to, you could change that to a decimal. Round it off, it would look like that. If I gave you that problem, I would accept either answer. I prefer 17 over 45. I try to keep it simple if possible. Okay, let's work on just setting this one up. Suppose that a cruise ship returns to the United States from the Far East, unknown to anyone. 4 people out of the 6,000 passengers have contracted a rare disease. Suppose that the Public Health Service screens 20 passengers selected at random to see whether the disease is present aboard the ship. What is the probability that the presence of the disease will escape detection? That means out of our sample of 20, nobody gets it. Okay, so let's start easy first. So on the bottom, that's a combination of, we've got 100 total. We're picking 20. On top, okay, so we had 4 of the 6,000 passengers. Oh, where'd I get 100 at? That should be 6,000. I'm sorry. And I'm picking 20 people. Okay, so if 4 have it, that means 5,996 do not have it. Okay, and I'm going to pick 4 there times the combination. There's 4 that do have it, but I'm not picking any of those people because it says when I do this, it's undetected. Okay, so that's my probability, and I'm going to stop there as far as I'm not going to waste your time on calculating that out. You should be able to do that by now. Okay, example 5. Rolling a die 5 times. A die is rolled 5 times. What's the probability of obtaining exactly 3/4? Okay, so just try to imagine, okay, we're going to do this 5 times. 1, 2, 3, 4, 5. So out of the 5 times, we want exactly 4 of them. Now let's just say those guys are the 4. So the probability of getting a 5 is 1/6. This is a little different. One of them, we don't get the 5. That means it could be any of the other ones. So there's 5 what I'd call bad ones out of 6. There's 1 good, 5 bad. Okay, so we would want to multiply those together, correct? Now there's one other thing. I don't know, I kind of set this up like the first one was the one that wasn't a 5, but it could have been any of them. So with that being the case, I've got to multiply by a combination of 5, picking 1. There's 5 spots and one of them will be the bad guy. So if I multiply all those together, my answer is going to be as a fraction, that's going to be 5 over 1, 2, 9, 6. Okay, so what if I change the problem and I say exactly, oh darn it, it said exactly 3 4s. I did 4 4s. So if I actually did the problem, I should have set it up this way. I want 3 of them, so that's a combination. Out of the 5, I'm going to pick 3 to be the 4s, and then I'm going to have 1/6, 1/6, 1/6. That's the probability of having a 4. Times 5 6. That's probably not having a 4. And when you multiply all that out, let's see, a combination of 5, picking 3. Should have did it in my head quicker. That's going to be 10. That number's 10. So it's going to be 10 times 5 times 5. So 25, 250 over, let's see, so I've got 6 6s, so 6 raised to the 5th. I got 7, 7, 7, 6. Why is that number? Oh, this should be 7, 7, 7, 6 also. I'm sorry. Now, it would not make sense to leave those as fractions. It'd probably make more sense to write that as a decimal because the numbers are so awkward. Okay, so let's talk about the complement rule. I talked about it already. So it says let E be any event, and we've got the complement of E. Okay, so the probability of E is 1 minus the complement of E. So, for example, if I said the probability using the rolling the die, let's say the probability of getting a 4 was 1/6, then the probability, if I put this in front, that means not 4, not negative, but not 4, that would be 1 minus 1/6, which is 5/6. That's kind of what I did up here with these guys. We just did in our head, but there's actually a rule that says that. So let's say if I had the probability of, I'm going to say, hitting a free throw. I'll just say probability of hit. Let's say that I know that that is 0.2719. Now, how did I get that? Well, I'm making it up, but remember we were talking about shooting free throws, and usually there's a manager that keeps track of that stuff. So we know the probability of hitting a free throw is 0.2719, which isn't very good. So if I wanted to find the probability of not hitting, so I'll put that negative, and that means not hit a free throw, I would take 1 minus 0.2719, and that would be 0.7281. So simply subtraction. Okay, now I'm going to use that here in a second. I got one more example in this section. This is kind of a good one. You guys have all been at a party sometime. You probably talk about this. I call this the birthday problem. A group of 5 people is selected at random. What's the probability that at least 2 of them have the same birthday? And we're talking about 365 birthdays a year, right? We're not talking about leap year, so take February 29th out of it. But there's 365 birthdays. Okay, so I want the probability of basically no matching birthdays. No matching birthdays. And if you remember, I did this earlier. Remember, I said think in terms of good out of total. Okay. I'm going to calculate this, okay? But I'm going to do this. When it says no, a good indication there means do the opposite. So if we did have matching birthdays, matching birthdays means you could have 2 of them that match, 3 of them that match, 4 of them that match, 5 of them that match. So matching would be 2, 3, 4, 5, 6. I'm sorry, just 5. It would not do us any good to talk about 1. Okay, so what I really want to do, I want to find the probability of 0 matching birthdays. And to do that, I'm going to take 1 minus all of these other ones. Hold on a second. I'm not saying this right. I want the probability at least 2 have the same. So it could be 2, 3, 4, 5, or 5. But that would be the same as 1 minus. I'm using that subtraction rule. 1 minus the probability that none of them match. Okay? So the probability that none of them match on the bottom, okay, so just imagine, and it might be better to do it like this. For the very first one, there's 365 possible birthdays. I'm going to take one person. That first person could have any one of the 365. Now we go to the second person. That person is going to choose any one out of 364. And the third person is going to be 1 out of 363. You know, I'm not liking how this is coming out. Let's do it this way. I'm sorry. Okay, so the total number of birthdays. This will be easier for you. Total number of birthdays would be, you have 365 for the first, 365 for the second, 365 for the third, 365 for the fourth, and 365 for the fifth, okay? That's 365 raised to the fifth, which is a really big number. I'm just going to leave it like that for right now. Okay, my top number, I'm talking about this right here. It's not 1. For the first person, they have a choice of 365 birthdays. But once you pick somebody there, you only have 364 next, then 363, and then 362, and then 361. So my probability of getting 0 would be equal to this number here, 365 times 364 times 363 times 362 times 361 over that 365 to the 5th. Okay, so give me a second. I'm going to multiply that real quick. That works out to be 0.9729. Now, when you go back to the problem, I want to know what's the probability that at least 2 of them will match. Well, using that property of subtraction, this is where I'm going to take 1 minus the probability none of them match. So 1 minus 0.9729. And that answer is going to be 0.0271. Okay, so I calculated the number of ways of not getting a match. That was this number. And I subtract that from 1. That gives me the probability someone will match. This is the probability no one matches. And down here, this is the probability at least 2 match. Now, you could take the probability 2 match, add that to the probability 3, plus probability 4, plus probability 5, but that's a lot more work. Once you get into it, this works out to be a lot easier. Sorry, I kind of messed that up in there, but you can see what it is now. And I believe it's the same what's in the book, so you should be able to follow that. Okay, that takes care of section 6.3. Got one more to do.